Greetings. My name is Kathy, and I'm a member of the Friends of Arlington's Planetarium. And we are trying to continue to provide you with some programming, some interesting things to do, even while the planetarium is closed and people are spending a lot of extra time at home. And so tonight we have an interesting program where Jim Edwards-Hewitt is going to be talking to us about the moon, which is something that everybody always loves. So I'm going to go ahead and let him get started with this and let him introduce himself, and won't waste any more time. Let's go ahead and get to it. Thanks, Jim.
Thanks, Kathy. So my name's Jim Edwards-Hewitt, and I'm also on the board of the Friends of the Planetarium. I'm a person who loves science and space and loves reading about science, like all of you. And I'm here to talk to you about how scientists figured out how the moon was formed, and also what that can tell us about how science and scientific theories work. From the time of that Galileo discovered the moons of Jupiter, astronomers speculated about how the moons and planets formed. But the first scientific theory that was proposed for the formation of Earth's moon was from Sir George Darwin, son of Charles Darwin, the famous biologist. George Darwin was a geologist who studied the tides, which are caused by the gravity of the sun and the moon pulling on Earth's oceans. Tidal forces also affect the solid parts of the Earth and the moon. Darwin figured out that these forces would transfer momentum from the rotation of the Earth to the orbit of the moon, causing the moon to slowly move further away from the Earth. Darwin realized that this meant that in the past, the moon had been closer to the Earth and the Earth had been spinning faster. It was also generally believed at the time that the Earth and the other planets had been molten or liquid rock when they formed, and then cooled down. Darwin reasoned that if you went far enough back, there could be a time when Earth was a blob of lava, and if it was an uneven shape, it could have been spinning fast enough to fling part of the blob into space, forming the moon. This became known as the fission theory. Fission means splitting apart. I mean, we talk about fission of atoms, but you can also have fission of planets. The fission theory was widely accepted by scientists for several decades. Darwin had worked out very well back to the point where the moon was orbiting close to the Earth, and less solid exactly how the moon spun off from the Earth, but there wasn't a better explanation. So people thought that seemed like a pretty solid idea. However, by 1909, some astronomers calculated that Darwin was incorrect, and a molten Earth could not have been spinning fast enough based on how fast the Earth and Moon spin to split off part of itself. And it became, most people agreed that, most scientists agreed that the theory didn't really quite seem to work. But even as late as the 1960s, there were still astronomers who were trying to figure out ways they could modify the fission theory to make it fit the facts. So other ideas came out, and by the 1930s and 40s, there were three main theories. First, as we said, there were still astronomers who thought the evidence supported some modification of the fission theory, the moon splitting off from the Earth. Others thought the Earth and the moon formed near each other as the solar system formed, orbiting around each other, the accretion or co-formation theory. And some thought that the moon had formed separately and was captured by the Earth, which was called the capture theory. And there, you can actually see a little variation in the diagram there. You can have the moon was captured intact by the Earth, or you can have the moon was broken up as it came near the Earth, and then it reformed in orbit. Now, to choose between competing scientific explanations, you have to fit all of the available evidence, and you have to explain your theory has to explain something that other theories don't. The problem was at this point that there just wasn't enough evidence. There was no good way to decide. However, even while things remained undecided, some new information was figured out in other areas about the moon. Edouard Roche was a French astronomer, and he also studied the tides. You find that a lot in moon scientists, especially early moon scientists. So as we said, it was generally believed at the time that the Earth's core was molten rock, all the way down to the middle. But Roche figured out from studying the motion of the moon around the Earth and the motion of the Earth itself that the Earth must have a solid core in the center, a solid core of iron. And other astronomers studying the moon figured out that the moon didn't seem to have a solid core, or at least not one big enough that we could detect it from here on Earth. And so that was an interesting new fact. Then Russian astronomers Evgeny Ruskal and Viktor Savronov challenged the idea that that planets were formed from the dust in the disk around the early sun, condensing straight down into molten rock and then cooling as a sphere. They instead proposed that the dust condensed into a lot of different sizes of rocks, and then these things, which were called planetesimals, would collide with each other. Sometimes they would break up, sometimes they would stick to each other, and slowly they would collide and merge over time. And in particular, the thing they figured out was that once a collection of planetesimals collided and fit together enough to be about 100 miles wide, its gravity would cause most of the other planetesimals in the same orbit around the sun to fall into it, and it would continue growing and grow into a planet. And over time, this idea also became widely accepted by astrophysicists. But at this point, we still don't have any solid way to decide between these three theories. None of them were considered proven. Each had evidence in favor of it, and each had problems. Now, the fission theory, we've already talked about its problems. They were discovered early on. The problem with the capture theory is that physics shows it is really difficult for a planet to capture a body as large as the moon. If it passed near the Earth, it's much more likely that it would be deflected and fly off into space, or that it would be pulled in by the Earth's gravity and collide with the Earth, as many planetesimals did and as meteors still do today. It's possible that to go into orbit if things are just right, but scientists really don't like theories that only work if everything is just right. And you're not explaining much if you have that. The difficulty with the co-formation theory turns out to be the opposite of the fission theory. The fission theory, things couldn't have been spinning fast enough for the Earth or moon to be flung off from the Earth. But with the co-formation theory, there seems to be no way that a collection of rocks around the same place orbiting the sun that's spinning would end up forming a moon that's going fast enough to be orbiting the Earth at the speed we see now. Bodies, would tend to be in kind of a slow orbit around each other because, they're a group of rocks that are in one place. And it's also hard to explain how the Earth would end up with a solid iron core and the moon wouldn't have one if they both formed from the same collection of planetesimals. So this was the state of things at the start of the Apollo program, when we actually sent men to the moon and could collect moon rocks and take all sorts of measurements and find out new things. But still, there was a lot of astronomers were pessimistic that we would ever find out enough to decide between these theories or really know how the moon formed, even after we collected material from the moon. Apollo astronauts gathered a lot of samples, moon rocks, lunar soil, and studied the craters of the moon and the maria, which are the seas that you see as the dark parts of the moon from Earth, like the Sea of Tranquility. So we found out many new things from that. We found out that from using radioactive element dating, that nearly all moon rocks are at least 3.5 billion years old, older than all but the oldest rocks on Earth. Meaning the moon's surface hasn't been changing from geological processes since that time. And the very oldest rocks on the moon and the Earth are nearly 4.5 billion years, which is almost as old as the solar system itself. The time of the planets were formed. But these oldest rocks and the very oldest rocks of close to 4.5 billion years tell us when the moon first began to form. And the next thing is that before Apollo, astronomers weren't sure if the moon's craters were from volcanoes or if they were from meteor impacts. And we were able to determine from studying them up close that nearly all the craters on the moon are from meteors. There's very little volcanic activity other than really early in the moon's history. But those weren't the biggest surprises. Studying moon rocks told us new things that didn't fit any of the theories that we had for the moon's formation. First, moon rocks and soil had no volatile elements, meaning anything that boils at a relatively low temperature. Now, we're not talking about things like water here, which boil away because the moon has no atmosphere. We're talking about metals and things like that that melt and vaporize at a lower temperature than you normally encounter in space. So Earth rocks do have these elements, which means that some process went on to cause them to, there was high enough temperature to cause them to escape into space that didn't happen to the Earth. Second, the minerals, by studying the minerals on the moon's surface and then other minerals, other rocks that were of a type that would have been thrown up from meteor impacts, scientists determined that there must have at one point been a giant ocean of magma just under the surface of the moon. And that based on the purity of the rocks that had been thrown up, it was 600 miles deep. And finally, the isotopes of certain elements, particularly of oxygen in moon rocks, closely match those ones on Earth. Meteorites that originate from different parts of the solar system that we found on Earth have different isotopes of oxygen, and this provides an indication of where the materials were formed. So this means that the material that makes up the moon must have been formed near the Earth. So now we're back to all of the theories are wrong. We can't even decide between them. The capture theory is completely out because the captured moon, the chances that it would exactly match the isotopes of Earth are so small that it's just not worth considering. And because it doesn't provide any explanation for where the massive amount of energy came from to produce that magma ocean. The co-formation theory is only somewhat weakened by the isotope problem. And it's unlikely that it could have produced the magma ocean, but it's not completely impossible. And the fission theory wasn't made any more unlikely by these discoveries, but it was already in trouble. So because the math didn't work out of the Earth spinning, and so it's also out. Nobody knew what to make of this right after Apollo. It wasn't until 1975 that American astronomers William Hartmann and Donald Davis and Canadian astronomers Alistair Cameron and William Ward came up with a similar idea by coming at it from different angles. They thought about, what if something big, like something that Hartmann thought maybe something bigger than the moon had slammed into the Earth, and it splashed, broken up and splashed, parts of the Earth and parts of that thing into orbit around the Earth. He presented this idea at a conference and waited for whether anybody was going to think it was a good idea when Alistair Cameron stood up. And he was worried that Cameron was going to shoot him down. But Cameron said he'd been working on the same thing, and it seemed mostly right, except that from his calculations, the thing that hit Earth would have had to be about the size of Mars, not just as big as the moon. But they both saw that this theory could explain all this new information we had. The planet that hit Earth, which was later named Theia, after the mythological mother of the god Mars, could have broken up when it hit, so that its iron core sank into the Earth and merged with the Earth's core. And the material that was thrown up from the outer parts of it would have less iron, which would explain why the moon does not have much of an iron core. A lot of material from the Earth would also be thrown up, and these would mix together. And so that could explain why there's the isotopes are so similar. And Theia, also likely to collide with Earth, would have formed at a similar distance from the sun, which is another reason why the oxygen isotopes would have been similar. The energy of this impact would have been converted into heat, melting or vaporizing much of the rock, and resulting, when the moon condensed, in the magma ocean in the early moon, and also contributing to the volatile elements evaporating and escaping into space before the moon cooled. If the impact was with a glancing blow rather than a direct hit, that would produce the amount of spin we see in the moon's orbit, and may have caused the Earth's axis to tilt to what we see today, which causes the seasons. Now, not everyone agreed with this new theory right away, and that's actually good. Scientific theories get accepted by scientists because they explain things well, not just because they're cool. There were still a lot of questions that needed to be worked out. So let's see. How likely is it that another body that large would form in the same orbit? Remember, scientists don't like theories that only work if conditions are just right. It turned out that computer simulations that Cameron and Ward did showed that as planetesimals came together to form an Earth-sized planet, it was actually likely that a Mars-sized planet would form in the same orbit and eventually collide. So how did all the material that was thrown up in the collision stay in orbit instead of falling back to Earth? Well, it turns out that tides are the answer again. After the impact blasted material into space, the Earth would have not been exactly round for a while because of this big chunk that got knocked away from it. And the tidal forces from that irregular shape would have dragged some of the material that was thrown off of the Earth along ahead of it, and given it enough additional momentum to stay in orbit and eventually condense into the moon. And if Theia was about the size of Mars, then only about 10% of it ends up being part of the moon. Some of it escapes into space, some of it falls back to Earth. Then there's the question of why didn't this happen anywhere else in the solar system? Remembering that scientists don't like just right explanations. And other planets don't seem to have moons that formed like ours or are as big relative to the main planet as our moon is. Well, if you look at how other planets rotate, it's likely some of them did have collisions, big collisions, just not exactly the same glancing blow as ours. And the exact angle and how directly things would hit is somewhat, is pretty much just by chance. So for example, the axis of the planet Uranus is tilted 98 degrees. It basically rotates on its side. So astronomers now think it probably got hit by several big things in the same around the same period in its formation, and got a more direct hit, so that whatever hit it merged with it and didn't end up in orbit. Venus rotates very slowly and in the opposite direction from most of the other planets, which was probably also the result of a giant impact. Again, one which didn't throw a resulting moon into orbit, but just merged with the planet. So it took a while for different astronomers to study the idea. It was pretty radical, but it actually wasn't rejected right away, which new scientific theories sometimes are, and they have to build up more evidence before people start to really consider them. If you're going to propose something really different in science, you need to have really good evidence, or as they say, extraordinary claims require extraordinary proof. In this case, there did seem to be really good evidence. A scientific conference about the origin of the moon was organized in 1983, which was just about 8 years after this was proposed. And they were expecting, they might still have, since it was a conference about the moon, different people have different ideas, that there might be a debate about the ideas. But it turned out that almost everyone agreed by that point that this really did seem to explain the evidence the best of anything they had. And it was called the giant impact hypothesis, and is still to this day the leading hypothesis for the formation of the moon. So, is that the end of the story? Just because people pretty much agree? Well, maybe not. Science is always looking for better answers. Astronomers Simon Locke and Sarah Stewart think that the giant impact hypothesis still requires conditions to be too much just right, with the angle that the body would have hit the Earth and how fast it might have been going. So they have a proposal that the impact was even more violent, and instead of breaking up and having rock become molten, that it was violent enough to vaporize a large chunk of the Earth and all of Theia, and that this would then form a giant cloud of vapor orbiting the Earth, which they named a synestia. And this would have slowly rained down on some small seed of rock that formed the moon, and a lot of this material would have come from the Earth, which would explain better how the isotopes match so well, and also they claim that this could be formed from Theia hitting from a number of angles, and not just one that matches well the current orbit of the moon. Astronomer Robin Kennup has proposed, instead of a Mars-sized planet hitting the Earth-sized planet, two similar-sized planets smashed into each other and were both blasted apart, and then the Earth recondensed and the moon recondensed from the debris. Now, neither of these ideas yet has wide acceptance, but that's how new scientific ideas start. Sometimes they fit the evidence and they take off, and sometimes they turn out to be interesting but wrong. Cool facts and pictures are great, and they're many of the things we love about science. But science is so much more. Science progresses by debating different theories, finding new evidence, and puzzling out how to interpret it. Some future astronomer may find new evidence that settles the question of the moon, or propose yet another theory that fits even better. Maybe it could even be you. So thank you. And if there are any questions, I'd be happy to answer them if I can. I mean.
I'm not seeing any questions from the audience right now, Jim, but I assume that these are the screen that you've got up right now gives us some links that people can go to find more information.
Yes. These are some of the sources I used that were quite interesting. And a lot of this material, I knew nothing about before I decided I wanted to know and started looking, especially in the early history of moon theories. So these are some of the best sources, and they will tell you a lot more.
Great. So you said that the oldest rocks on the surface of the moon were about 3.5 billion years old. Is that when they think the moon itself was formed?
They seem to think that the moon, the collision happened almost 4.5 billion years. So I'm actually not entirely clear. It seems to be that the moon cooled relatively quickly. So I'm not entirely certain what was going on for those, for that billion years. I mean, there are rocks on the moon. The really, really old rocks they found on the moon are more than 4 billion years old.
And originally, after this initial collision, the moon has not always been where it is now, right? It it has moved over time. It's
Yes,
changed
yes.
its
So
orbit.
George Darwin was right about that part. The moon was quite close to the Earth when it first formed. It's right now it's 238,000 miles from Earth. Um, it's believed that when it first formed or soon after, it was probably 15 to 20,000 miles from Earth. So it would have, it would have been really big in the sky if you were here then. Um, and the Earth probably was rotating at about every 5 hours then, and the moon was orbiting maybe every 14 hours instead of every 28 days.
So, so is it still moving further away now?
It is. It's when it first formed, it was close enough that the tidal forces were strong, and it moved away fairly quickly as in geological terms. Now it moves, I believe, a couple of inches a year. But we're still getting, the tides are still transferring momentum from the rotation of the Earth to the orbit of the moon. And, hundreds of thousands or maybe millions of years in the future, um, the moon will be, you'll only see the moon from one side of the Earth because it will orbit the Earth. The Earth's rotation will slow down, and the moon will move further away, and it will orbit the Earth once every Earth rotation.
But that's not going to happen anytime real soon, is it?
No, no, it's only happening a few inches a year, so it's going to be many, many, many years, several million years, I think.
Okay, well, I think that's probably about all the time we have tonight. I'm not seeing any questions at the moment. I want to thank you for giving us this talk tonight. The recording will be available. And we hope that you will tune in and look at our next live event. Keep looking on our Facebook page for more programs, and we hope to see you soon. So until then, thanks for watching, and bye bye.
Thank you.